with study goal number 21. I'm going to leave 22 and 23 for another day of school. That's for a week from today. So today I'd like to do study goal number 24, and please look up. I'd like you to format number 24 like this, with rivers on the left and canals on the right, and physical, ecological, and human characteristics.
Wait, does the ocean frozen stuff right to the right of it, does that have anything to do with
No.
Okay.
If you want to look up number 24, I have some bullets. River physical properties, canal physical properties, river ecological systems, canal ecological systems, river human benefits, canal human benefits. This also connects with our warm-up today.
What was the last one? Ecological and
Human. I think that this will be a good setup for our field trip next Monday. I think I mentioned this in class last week, that modern cities are built to dump water because we're solving problems that the cowboys dealt with. You all remember that? For today's warm-up, streams can be really clumsy for people who live near them, because streams can get clogged with like a tree or trash or a rock, and they flood a lot. Has anybody ever lived near a stream and experienced flooding or other problems from your stream? Pretty much everybody who's lived near a stream has had problems. That's also been my experience. I've lived near streams often. And streams are awesome, and they're all like, they make good sounds, and every now and then you see baby ducks, and everything's cool. Except when it rains really hard, some rock will shift and your stream floods, or the stream has like a blowout and like your deck falls in, or chaos ensues. Streams are nice and everything for the baby ducks, but they're not really helpful for cities. Remember, there are problems we get from having water around. You should know them. I can think of 3. Problem number 1 is disease. Like a lot of illnesses live in stagnant water, or disease vectors breed in stagnant water, like mosquitoes like pools of water to make their babies. So stagnant water spreads disease. Flooding can damage our construction, our houses and our businesses, our bridges and our roads. And flooding can be dangerous for transportation, either causing accidents or delays. So for the warm-up, you can dig up your stream and make it into a gutter, like that one. That used to be a stream. That actually used to be a river. This is called the Los Angeles River. I lived near the LA River when I first came to the United States. And through Los Angeles, the LA River does not look like a river. It just looks like this or bigger. And it's just a drain. Get rid of the water. Keep us healthy so we don't get the spread of disease, protect our construction, maintain our transportation. And really, canals are very, very good at that. Dry cities are kind of nice to live in, practically speaking. study goal number 24. I want to compare the original creek with a canal. And on our field trip next Monday, we're going to do this. On our field trip next Monday, we're going to start on the Mission Creek watershed where the creek is intact. And we're going to go downriver as Mission Creek becomes a canal. And you'll see that transition, and maybe you'll see some of the problems I want to tell you about.
The river are you classifying river and stream as the same thing?
Yeah, I'm pretty sure that's just a matter of scale. So, stream and river might be in the eye of the beholder. I'd be curious if there's like a critical definition, I don't know. But I've always thought rivers are just small streams, or streams are small rivers. All right. Here's that comparison. That table that you made, I want to talk about rivers and then canals in each of those three categories. First, we'll talk about their physical makeup. If you've ever been to a river, you'll know what I'm talking about. 4 bullets. Rivers or streams have habitat diversity. You'll see gravel, rocks, sand, deep spots, shallow spots, riffles, pools, waterfalls, cascades, shady, sunny, clean, dirty. Rivers have a bunch of different little pockets. There's a little of everything. Habitat diversity. Something else that rivers have is lots of vegetation. Because rivers are permeable, everything that grows next to the river gets watered. That's called riparian vegetation. Vegetation along the river. We talked about how important that is. You might remember when we talked about the elk and the wolves in Yellowstone. Number 3, there's something interesting about rivers that I'll bet you've never noticed. But because rivers are mostly shaded, and because rivers have a lot of organic material that insulates them, and because rivers have a lot of deep pools, rivers tend to have a very consistent temperature. Ecologically, that's a really big deal. As a physical property of a river, it's remarkable that their temperature is very stable. They're shaded, they're naturally insulated, they have deep spots that hold their temperature well. Finally, number 4, because of all the surface action, rivers have very high dissolved oxygen levels. This is kind of a news flash, I guess. Gases dissolve into water. They're called dissolved gases. They don't bond with the water like there's O2 in water. It's dissolved. So those molecules are just bouncing around inside the field of liquid. And because rivers have a lot of surface activity, they get a lot of oxygen dissolving into the water. We'll talk more about dissolved oxygen later, but I need to start with that here. Now, if you look at the picture on the screen, you can imagine that the physical characteristics of a canal are exactly the opposite. There's no habitat diversity. There's no riparian vegetation. When the sun comes out, the temperature spikes, and when the sun goes away, the temperature plummets. So you have what's called extreme temperature variation. Finally, if you look at the surface of that water, because it's so still, you had very low oxygen levels.
Wait, why would it have low oxygen levels?
So, this explanation is unfortunately infinite. I could talk about this until long after either of us stop caring. As an easy principle, the amount of oxygen that you can fit into water depends on how much you stir them together. So maybe you've seen that for small fish tanks, people will often put like a little air stone in there to make little bubbles. That's just to stir up the water, and that activity dissolves oxygen into the water so that the fish can breathe. Just like you have water inside your lungs, we all breathe from dissolved oxygen, just like fish do in water. We just carry the water with us. And if you can't get enough oxygen into that water, then the levels of oxygen in your blood start to go down. So ecologically, dissolved oxygen is really important for productivity and for stuff to live in that water. I'd like to compare the ecology of rivers and canals, and you can probably guess where this is going because it's obvious. Canals have really complex food webs. They have a lot of productivity.
Rivers do.
Crap, thank you. That's the disease talking. So river, oh god, now I'm gonna die. Rivers have complex food webs, they're very productive. They have decomposition, they have a nursery effect, where a lot of babies can feed and grow up in rivers. Maybe you know that salmon put their babies into rivers, that little ducklings like to play in rivers. Say again?
I said dumplings too.
Not dumplings, ducklings. But you can make dumplings out of duck.
Really good.
Duck fat is tasty. Children, if you ever get a chance, you should render ducks and make a jar of duck fat and then make French fries with duck fat.
Maybe over the weekend.
Just saying.
You sound like
But
he's
like
white
the ducks
in
that
the
like
office.
you eat are like the mallard ducks. I mean,
What?
you don't eat mallard ducks that you eat like different ducks.
Mallard is actually a spectacular duck. Of all the ducks, mallard
No,
is
but
one
like
of the
when you
most
get served it in a restaurant, you usually don't get like.
If you serve that in a restaurant, people would complain that it's a bit gamey and tough. So farmed duck is Asian duck species that's not common in North America. But wild duck tastes a bit leaner, less fatty, and a little bit stringier because they fly more. It tastes more white meat, less red meat. Wait. I'm ready to make this. More red meat, less red. Duck. Anyway, rivers. Complex food webs, highly productive, decomposers, nursery effect. Whereas canals have no ecological function whatsoever. Canals are generally lifeless. Canals tend to be lifeless. And I should point out that's kind of a big bummer, because rivers are like the circulatory system for life. Everything on land interacts with water. So when you sterilize the river, that can have really big ecological impacts. Now these all matter to humans too. Strategically, something that's really nice about rivers for humans is that rivers improve water quality. They recharge groundwater. They give us recreation. And they slow flooding. At least some of the time. Bioremediation, recharge groundwater, recreation, and flood control. By the way, flood control because they slow down the water and they absorb a lot of the water. Now, the interesting thing about canals is there's a little social justice here. Like, in your neighborhood, if you have a canal, that's probably in your best interest, because that gets the water out of your neighborhood. But if somebody lives downriver from you, then that's like living underneath somebody else's toilet. So when we talk about canals and humans, I want to remind you that there might be people downriver. Canals flood pollution onto those people. They flush all your turds onto them. So flushing pollution downriver. They also prevent your flood by dumping all your water to whoever's downriver. So you can just shift your flood to become their flood. Right? Like if you're down the canal from me, all the water runs off my house so I can go play hopscotch. And now all that water's been delivered to you, plus what you just got in the rain, you're going to get the flood. And of course, canals are not as recreational. So it's kind of a crappy trade. And all over the world, people are realizing this. But of course, we built our cities a long time ago, so they all have this outdated solution to problems that aren't that big of a deal. I want to leave this on hold for now and return to these topics when we go on our field trip on Monday next week. Are there questions on study goal 24? Yeah.
Are there any pros of canals?
Well, honestly, the disease and the flooding and the construction stuff, like once you've built your city right up to the rivers, you kind of have to channelize them. You know, in many parts of Europe, rivers had a lot of cultural value while cities were being built. So in many parts of Europe, instead of putting the houses right up to the river, there would be houses, then like floodplain, and then the river. And so in cities that were built with a little bit of buffer away from the river, those rivers already handle all the problems without the trade-offs. Whereas most of us in the United States, we've built our houses literally up to or over the river. This used to be a creek, pretty much right underneath that door threshold. Used to be a place called Laguna Creek. The Civil Army Corps of Engineers, they just piled up rocks and built our school on top of a creek. If you go on the lower west side, you can see Mission Creek flowing through people's backyards, and there's just like a fence that's just like on a wall that is the canal. If you live right there, you love your canal because the alternative would be a disaster. So there's benefits now that we've built ourselves into that position, but we're also stuck with the problem. For study goal number 25, I'd like to return to the dissolved oxygen stuff. So I want to switch to assignment 8.3 now. What? 7.3. I'm basically a total mess, and I apologize for that. Questions on the vocab in 7.3, please. Leventhal?
Indirect water reuse.
Okay.
Reuse.
There are 3 types of reusing water. I gotta define all 3 of them. So reusing water directly means you're taking the wastewater and you're doing something with it. Like in Santa Barbara, we directly reuse about a quarter of our wastewater to irrigate stuff downtown. That's direct, and that's probably obvious. Indirect is putting your wastewater into the ground so that later on your groundwater will have extra water in it. And it's all just blended together by the groundwater. They do this in Orange County, where they have all their water treatment facility, and then they just dump it into these big surface ponds that just soak into the ground. They just take all their wastewater, instead of putting it into a river, they reuse it by just trickling it into the ground. And that'll usually filter it, and it'll dilute it with a bunch of other groundwater. So by the time you use a well, you've got indirectly some wastewater in it. And inadvertent is when you are reusing water by accident. Maybe you didn't even know it. Like somebody up the river was dumping sewage into the river, and by the time it gets to you, it's like, well, I guess this is our water. Or somebody's watering a farm, and then you didn't even mean to, but that's going to add some groundwater to you. So inadvertent is kind of accidental or unintentional. Does that make sense? Other vocab? What? Bioswale are man-made creeks. We saw some on the UCSB field trip when we were like walking up to Manzanita Village from the lagoon. Yeah.
Ecosystem effects?
I can't remember what that is. I gotta check the book.
Effects as a result from interactions in an ecosystem.
Yeah, that sounds right, but I still have to check the book to remember the context on that one. You have to ask me when we get to the day before the exam. Other vocab? This came up in period 1, I also didn't remember. Anybody else? Other vocab? Assignment 7.3. Last call. Yes.
Just like a question, like, is like eutrophic and oligotrophic, are they like opposites basically?
They are opposites. Oligotrophic is low nutrient, and eutrophic is high nutrient. We have a lecture about this coming up, but high nutrients can be natural, like wetlands just have a lot of nutrients in them because of all the debris that goes into them.
Yeah.
But also, eutrophication can be cultural, like humans do that. So if you put a bunch of wastewater into a river, that's going to take too many nutrients down there. Last call for vocab. So children, in assignment 7.3, a lot of the study goals are specific to other lectures I have planned in the unit. So I just want to skip through 7.3 and pick up the study goals that are not going to come up later in the unit. So I'm going to skip through, and I'm going to try to go in order. Here we go. Number 26 and 27 I'm going to skip for now. Number 28, the answer is poop. This is like the shortest answer that you'll ever have in Apes. And it's unambiguous. If anybody ever says coliform bacteria, that's poo-poo bacteria. If you have like coliform bacteria counts are high at the pit, that means there's turds at the pit. Nobody wants to call it poo-poo. So we specifically discussed the bacteria that make you sick, but they make you sick because you're not supposed to eat other people's poo-poo. So if you ever hear about coliform bacteria levels, that means there's turd in the water. Now here's something that's interesting. Just to give you a sneak peek of tomorrow, or Thursday, interesting sneak peek. If you put a dukester into a healthy river, the poopy bacteria will die. But if you put a dukester into that canal, the coliform bacteria will explode. Hey!
Is there a Katie in your 5th period? Bears?
What?
Bears?
need to remind you of something. That coliform bacteria lives in places with no oxygen, like your intestines are anaerobic. That's why you can light your farts, because carbon sticks to hydrogen and makes methane, so you can light your farts, because it comes out of your arse, which means it's from your intestines, which are anaerobic. Remember, coliform bacteria live in anaerobic environments. Write that down. Coliform bacteria live in anaerobic, no oxygen environments.
How do you spell it?
Just go for it. Add an A somewhere.
Anyway.
You ready?
I got it.
Anaerobic.
Oh, okay, we're good now.
Anaerobic.
Forgot the E. It's okay.
Poopy bacteria do not survive in high oxygen environments because they come from your butt where there's no oxygen. Okay, number 29. When I was your age, there used to be all these tanker ships that would crash into rocks and spill oil everywhere. And your generation has basically lost this problem. In the last 30 years, we've been building new types of tanker ships. So for number 29, we have made oil tankers have double holes. There's a boat inside the boat. Today, if a tanker ship hits a rock, it might get a hole in the outside, but not a hole in the inside. Back in the day, we used to have these boats like this. Look at my hand. And they would crash onto rocks and all the oil would come out. But now we've got these ones. So if they crash onto rocks, who cares? There's still a separate hole. They're called double holes.
Hull as in Hull.
Correct. Also, we route oil tankers further from shore. When I was a little grom, we would go down to the beach and we could see oil tankers cruising down the coast. Now it's really tough to see oil tankers. You rarely see them. Even in the shipping channel, we've got cargo ships, but not really tanker ships. Number 30, I don't have the energy to do today. Number 31, I would like to talk about. Oh, God, I'm dying. Oh. And number 31, I'd like you to write this first. Oxides plus water makes acids.
With the minus sign, or is that just there?
That's just little indicators on the sides. Sorry. Oxides plus water equals acids. Technically metallic acids, but whatever. Please look over here. Jose smells. Also, when I say oxide, I mean something with oxygen atoms stuck to it. So that's carbon dioxide, nitrogen monoxide, nitrogen dioxide, nitrogen trioxide. We call these NOx because that X represents any number. So it doesn't matter how many oxygens you have, they're all called NOx, nitrogen oxides, plural. Everybody okay with that shorthand? If I put an X, that means any number? So SOx means SO1, SO2, SO3, and SO4? SOx? We don't really say that for the carbon oxides. Hey-o! Raise your hand if you've seen Kill Bill.
That's my favorite.
Quentin Tarantino, Uma Thurman.
One of them. Oh my god, it's so good.
There's a scene in one of the Kill Bill movies where Uma Thurman is buried alive.
Oh,
Yes.
Second.
What happens when you are buried alive? You suffocate. Can anybody explain to me why you suffocate underground? Why?
Because
The
you're-
oxygen can get you through the dirt.
So, I need everybody to just not write any notes and just stay with me for a moment. Topsoil is porous. Topsoil has little air gaps. Topsoil gets stirred up by critters. So topsoil is actually oxygen rich, just like the atmosphere, 19%.
But you end up breathing in the soil.
But if you get a bit deeper and deeper and deeper, there's more and more packing of the soil, so the oxygen gets used up. Once you get into rocks and stuff, there's no oxygen down there. Next. If I bring a shovel and I start digging stuff up, the top few inches have had oxygen around all day. If I go a foot down, that saw oxygen last week. But by the time I get 2, 3, 5, 10,000 feet down, those rocks have had no oxygen for a very long time. Does that make sense to everybody? And you can imagine, if I dig up a piece of like aluminum and I throw that onto the surface, now this aluminum has never seen oxygen, but now it'll oxidize. It's going to interact with oxygen because in the atmosphere there is oxygen. Are we okay with that? To oxidize is to interact with oxygen? Yeah? So I have taken what used to be a piece of buried aluminum and I have now brought it to the surface and it's become aluminum oxide. Technically aluminum's a horrible example, but anyhow. Maybe you know that you have to keep oil on cast iron skillets or they'll rust. Maybe you know that like a wood burning stove, if you paint it, will not get rusty, but if you take a wood burning stove and leave it outside and the paint flakes off and it starts to get all rusty, that's oxidation. Are we all okay with that? Iron is an obvious oxide, visible. Here's why that matters. Every mine is a hole in the ground. Every mine, whenever you take something out, is going to interact with oxygen and make oxides, and then when it rains, you get acids in the runoff. Please look up. It's called acid mine drainage. Study goal number 31. Acid mine drainage. Because you dig things up, they interact with oxygen, they become oxides. When it rains on them, there's acid in the runoff. Like this. Tar Creek in Oklahoma was extremely famous because the river leaving a mine in Oklahoma got down to like a pH of 3 point something or 4.1 or whatever. That's like pure hydrochloric acid. Like you throw a fish in there, the fish would dissolve.
What happens if you step in it?
I think it would hurt a lot.
Okay.
I think it would be devastating for your skin.
Look at that beautiful riparian vegetation.
Yeah. This was a really famous mine. They did a lot of mining back in the day before environmental protections. Like, you can fix this. Like, if you just cover up all your oxides so it can't rain on them, that's all right. Today, we've got laws to prevent this. Today, if you dig up a hole, you're supposed to take everything that you dug up and cover it with dirt so that it won't oxidize. Hey. But we learned the hard way in this one really famous place in Oklahoma called Tar Creek, where they had a whole bunch of metals from in the ground and they made a ton of acid mine drainage that really polluted a creek. Anybody curious to discuss that anymore?
Is that something we'll need to know for the ink test?
It's impossible for me to say, but it's like the most famous acid mine drainage site on Earth.
So it's something that they would put on it.
I believe acid mine drainage has come up repeatedly. One context in which it comes up a lot actually is those tar sand mines, because you're digging up so much rock and then you're lighting it all on fire to melt out the petroleum. That makes huge volumes of oxidized material, and so if it ever gets wet, then there's like horrible acid mine drainage from tar sand extraction. I want to do number 33, and then I'd like to die. 33 starts with a story. All over the United States during the baby boom, we were building roads, we were building suburbs. Everybody bought cars because our economy was raging and everybody was getting a raise, and we had all of this economic excitement. So with all those suburbs and all those long drives and all those new American muscle cars, in the baby boom we started building hell of gas stations. Bazillions of gas stations. Almost every single gas station in North America was built right after the baby boom in like a 20-year period. And back in the day, the way that you built a gas station, you make a swimming pool, like concrete. You put a lid on the swimming pool, and then you put some pumps on top. And you fill that swimming pool with gasoline, and when Jose drove up, he'd go click, click, and it would go, and it would pump the gasoline out of a pool underground, and you'd put it in your car. Concrete tanks. And then in the 1970s, all the hippies started complaining, and we got worried about air quality. So we started putting additives in gasoline to make them cleaner for the atmosphere, and those additives dissolve concrete. And we only found out because our groundwater started to catch on fire. America. If you pay attention, almost every single gas station in Santa Barbara has been dug up and rebuilt in your lifetime. Because sometime around the late 90s, middle late 90s, people were like, why gasoline in groundwater? Over there too, over there too. And then we figured out that our gas storage and gas stations was stupid. So fun fact, the #1 pollution of groundwater in the United States is gasoline. And as a matter of fact, you have to know that. So the #1 pollutant found in groundwater is gasoline. Here's what's interesting. If you take groundwater from the bottom of the aquifer, you're fine, because gasoline floats, because it's a very light liquid. And the way that we get rid of America's gasoline in groundwater is we use what are called extraction wells. Please look up, which only go to the very, very surface of groundwater. They slurp at the top. And gasoline floats. Does that make sense to everybody? If you want to skim off the gasoline, you take it off the top of the groundwater, right at the water table. So extraction wells pull out gasoline from the surface. There's another interesting thing about groundwater that's especially problematic here in Santa Barbara. This is a big problem for us. By the way, I think it's a big problem for Israel as well. Please look up. I made you a drawing. Here's land. Here's the ocean with the double shock breakers. Here's groundwater, and there's a well. Now, usually, groundwater is higher than sea level because it's on its way out to the sea. Everybody understand what I'm saying? Normally, groundwater looks like this. Please look at the screen. you can see that the groundwater is kind of piled up above sea level because it's on the way to sea level. Does that make sense to everybody? Now imagine, if you're in Santa Barbara, you're on the coast, if you start to remove groundwater, then by creating a cone of depression in the groundwater, sure, some groundwater will refill that cone of depression, but maybe the salt water will sneak in. Please look up. If you extract too much groundwater, watch this. I'm going to do a quick shift. Watch the screen. Pow! You can ruin your groundwater by sucking out too much. It'll be replaced with salt water. That's a big problem for Santa Barbara because you all realize we're right at sea level. And we got a whole city that uses groundwater. So we deal with this thing called saltwater intrusion, which is a vocab term for number 32. Saltwater intrusion is when sea level sneaks into your aquifer because you took out too much fresh water. Now I'd like to dive into these. Are there any questions about these study goals? Everything else we'll hit on a later date. Liam, we can stop recording.